The economic dispatch of power plants, theory and practice. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I'm going to present to you the fundamentals of economic dispatch of power plants. We are going to begin with a quick review of the theory and subsequently solve 7 practical exercises. Let's go to case 1. Case 1 is that in which several generating units of a single power plant are dispatched to feed a load center. The cost of operating a generating unit in dollars per hour in terms of the power output is the cost is equal to AP squared plus PB plus C, where P is the power output and AB and C are cost coefficients. For the aggregate operation of several generating units in a power plant with different operating costs, the incremental operating cost of each unit is this. The incremental operating cost is the derivative of this function, of the cost function. That is the derivative of C with respect to P, the power, is equal to the derivative of this, 2 times AP plus B dollars per megawatt hour. Okay? And we arrive at our optimization problem. Suppose that there are many generating units in a power plant dispatched to feed a load. The power that has to be delivered to the load is the demand, okay? And the generating units will be dispatched to feed the load. The power delivered to the load, the demand, is the sum of the individual powers. What we want is to minimize the cost. This is our optimization problem. We want to minimize the cost, and the total cost is the sum of the individual costs. We seek the minimization of the total operating costs subject to generation constraints. And after we carry out this optimization, we find this, the economic dispatch. For economic dispatch, all units must operate at the same incremental operating cost. Okay? When this happens, we have optimal dispatch. That is the derivative of the cost of operating generating unit 1 with respect to its own output power has to be equal to the derivative of the cost of operating generating unit 2 with respect to its own output power, and so on. When they all are all equal, then we have optimal dispatch. Okay? That's the theory. Let's go to exercise 1 now. Now let's begin with the exercises. Exercise 1 says, consider a power plant having 2 operating units. Their operating costs are given by the following cost functions. C1 is this in terms of the output power, and C2 is this in terms of the output power. And the cost functions are given in dollars per hour. Letter A, determine the economic dispatch schedule and the corresponding cost of generation for a demand of 180 megawatts. Letter B, if the load is equally shared by both generating units of this power plant, determine the savings obtained by loading the units optimally. Okay, my friends, this is the question. Let's go to the solution. We are going to begin with letter A. For economic dispatch, as we saw, for economic dispatch, the incremental costs of each generating unit have to be equal, okay? That is IC1 has to be equal to IC2. They must operate with the same incremental cost. And this is the derivative with respect to the power output of generating unit 1 of the cost of operating generating unit 1 has to be equal to the derivative with respect to the power output of generating unit 2 of the cost of operating generating unit 2, okay? So, what did I say? I said that the derivative of C1 with respect to P1 has to be equal to the derivative of C2 with respect to P2. When this happens, they are optimally dispatched. Calculating, we find that IC1 is equal to 0.6 times P1 plus 50, and IC2 has to be equal to 0.4 P2 plus 30. Alright? But we already know, and the exercises say that this is the condition of letter A, that the load is 180 megawatts. Additionally, we know that P1 plus P2 is equal to 180. We are going to solve this system of equations. Combining these two here, we find here that 0.6 P1 minus 0.4 P2 equal to negative 20. That is the system of equation here that we have to solve. And we find that for the case of a load of 180 megawatts, P1 is equal to 52 megawatts and P2 is equal to 128 megawatts. Okay? Substituting the values in the cost functions, we find that what we need to do is to take this value of P1 and put here. Okay? Simply, you take this value of P2 and put here. Okay? And when we do this, we find that C1 is equal to 3,511.2 dollars per hour, and C2 is 7,266.8 dollars per hour. These are the costs of operating the generating units. The cost of operating generating unit 1 is $3,511.2 per hour, and the cost of operating generating unit 2 is $7,266.8 per hour. All right. Now let's go to letter B. Letter B wants us to compare the case in which the load is shared equally between the generating units and when they are optimally dispatched. This is optimal dispatch, and this is not. We are going to see why it is not. Okay? If the load is equally shared, P1 is equal to 90 megawatts and P2 is equal to 90 megawatts as well. The total cost of generation is going to be, we are going to do the same as we did for this case. We are going to take this 90, substitute here, and this 90 substitute here, and we are going to find that the cost C1 will be equal to $7,030 per hour. Simply take the value of the power and substitute here, okay? C2 is equal to $4,470 per hour. Summing then, we have a total cost equal to $11,500 per hour. All right. And if we sum this, the total cost will be $10,778 per hour. And what is going to be the saving? The savings when we operate then optimally rather than when the load is shared equally is going to be, let's put it CT2 and CT1. CT2 minus CT1 will be equal to this number minus this number, and it is $722 per hour. We are saving $722 per hour when we dispatch them optimally rather than when we share the load equally among the generating units, okay? Which translates to approximately, and this is per hour. Per hour, the exercise wanted us to calculate per hour. But what if we wanted to calculate per day or per annum? Okay, per day will be per day will be 17,000, and per year 6 million dollars. Okay, this is the result of the exercise. The exercise wanted us to calculate the savings per day, but if we extend what we learned, we can observe that it is per hour, per day. In a year, we save $6 million, okay? This is the conclusion that we get while solving exercise 1. Let's move on to exercise 2 now. Exercise number 2 now. The cost functions of 3 generating units of a thermal power plant are as follows. These are the cost functions. And if the generating limits of these units are as this, question, find the optimal dispatch schedule for a load of 1000 megawatts. Okay, my friends, this is the question. Let's go to the solution. As we saw, for optimal dispatch, their incremental costs have to be equal. That is the derivative of C1 with respect to P1 has to be equal to the derivative of C2 with respect to P2, which has to be equal to the derivative of C3 with respect to P3. Okay? This is the condition for optimal dispatch. And since the exercise stated that the load center has a demand of 1000 megawatts, P1 plus P2 plus P3 will be equal to 1000. What we need is to differentiate. We are going to differentiate C1 with respect to P1, C2 with respect to P2, and C3 with respect to P3. And we are going to find the following equations. 0.8 P1 plus 10, okay? This is the derivative of C1 equal to 0.7 P2 plus 5, which has to be equal to 0.95 P3 plus 15. And the other condition is this. P1 plus P2 plus P3 has to be equal to 1000. We have a system of equations. And after solving this system of equations, we find that P1 is equal to 334.38 megawatts, P2 equal to 389.29 megawatts, and P3 equal to 276.32 megawatts. But there is a mistake there, okay? Actually, the solution is right. It is correct, but there is a mistake there. What is the mistake? The mistake is here. Because we are violating the upper limit of generating unit 3. Observe that unit 3 violates its maximum limit. Therefore, we need to set P3 at 250, and the remaining load is going to be shared optimally among generating units 1 and 2. Okay? Then this is not the solution. The solution will be 250 here, and we are going to solve this again for this boundary condition here. And we are going to use this and this here only. These two here only. Okay? But P1 plus P2 will be equal to 1000 minus 250, because we already stipulated that P3 has to be equal to 250, and this is 750 megawatts. Solving again, we find that P1 is 346.67 megawatts, and P2 403.33 megawatts. Okay, this is all for exercise 2. Let's go to exercise 3 now. Exercise number 3 now. Consider a thermal power plant with 2 generating units with slightly different operating cost characteristics as follows. This is the cost of operating generating unit 1, and this is the cost of operating generating unit 2 in dollars per hour, in which P1 and P2 denote power outputs in megawatts. The questions now. Letter A, find the optimum load allocation between the 2 units when the load demand is 162.5 megawatts. And letter B, what will be the daily loss if the units are loaded equally? Okay, my friends, this is the exercise. Let's go to the solution. For letter A, we are going to calculate the optimum load dispatch. For optimum economic dispatch, the incremental costs of operating generating unit 1 and 2 have to be equal, as we saw in the previous exercises. What does it mean? It means that the derivative with respect to P1 of C1 has to be equal to the derivative of C2 with respect to P2. Okay? The derivative of the cost of operating generating unit 1 with respect to its own power output has to be equal to the derivative of the cost of operating generating unit 2 with respect to its own power output. When this happens, we are dispatching them optimally, and we are going to take the derivative of this and take the derivative of this, and it becomes 0.8 P1 plus 160 equal to 0.9. P2 plus 120. The other boundary condition of this exercise is that P1 plus P2 has to be equal to 162.5. Okay, we are going to solve this system of equations, and when we we find the solution. The optimum dispatch is when P1 is equal to 62.5 megawatts and P2 is equal to 100 megawatts. Alright, this is the optimum dispatch. Now in letter B, the exercise wants us to compare the cost of operating them when they are optimally dispatched or when the load is shared equally. Alright, when the load is shared equally, P1 is equal to P2, which is equal to 162.5 divided by 2, which is equal to 81.25 megawatts. Alright, if we use the production cost functions for 81 megawatts, we are going to find, when we substitute this 81.25 megawatts here, we find that C1 is equal to 15,640.6 plus K1, and C2, we are going to substitute this here. We find that it is 12,720.7 plus K2. Okay? These are the cost functions for the value of 81.25. That is when the load is equally shared between the generating units. Okay? With these values, we can calculate the daily loss. The daily financial loss is calculated as the loss is going to be equal to 24 hours, because here they are expressed in dollars per hour. If we want the daily financial loss, we have to multiply by 24 hours, and it is going to be the difference between T when P1 is equal to 81.25 and P2 equal to 81.25 minus CT when P1 is equal to 62.5 and P2 is equal to 100 megawatts. Okay? The difference between these times 24 hours is the daily financial loss. Alright? See, this one here is this. CT when P1 and P2 above 81.25 is equal to 28,391 plus K1 plus K2. You simply sum them, okay? You simply sum them and you find this. Now, calculating this, the total cost for the optimum allocation, okay? We simply substitute 62 here and we substitute 100 here, and we find that CT for the case when they are optimally dispatched is 28,062.5 plus K1 plus K2, okay? And the difference between them is going to be the loss per hour multiplied by 24 is the daily loss. And the daily loss, you simply put this here and this here, and the loss will be equal to 7,891.2 dollars per day. All right, what is the conclusion that we get? If the generating units are equally loaded rather than optimally loaded, there will be a financial loss of 7,891.2 dollars per day. Okay, my friends, this is all for exercise 3. Let's go to exercise 4 now. Exercise number 4. A power plant has 3 generating units with the following cost characteristics. These are the cost characteristics of the generating units, in which P1, P2, and P3 are the output powers of the generating units in megawatts. If the maximum and minimum allowable loading on each unit are 150 megawatts and 39 megawatts, the question: find the economic dispatch schedule for a total load of letter A 320 megawatts and letter B 200 megawatts. Okay, my friends, that's the question. Let's go to the solution. From the cost functions, these are the cost functions. From the cost functions, we obtain the increment cost characteristics. What is the incremental cost? The incremental cost is simply the derivative of each of the cost functions. Okay? So the incremental cost of operating generating unit 1 is the derivative of C1 with respect to P1. Okay? And this is equal to P1 plus 215. Alright? This is in dollars per megawatt hour. The incremental cost of operating generating unit 2 is the derivative with respect to P2 of the cost of operating generating unit 2. And this is equal to 2 P2 plus 270 dollars per megawatt hour. Similarly, the incremental cost of operating generating unit 3 is the derivative of C3 with respect to P3, which is equal to 1.4 P3 plus 160 dollars per megawatt hour. For economic dispatch, they have to be equal. That is P1 plus 215 has to be equal to 2P2 plus 270, which has to be equal to 1.4 P3 plus 160, and we are going to call it lambda. Okay? And we are going to write then in terms of lambda. P1 will be equal to lambda minus 215. P2 will be equal to lambda minus 270 over 2. And P3 will be equal to lambda minus 160 divided by 1.4. Okay? The boundary condition of letter A is that letter A here, P1 plus P2 plus P3 has to be equal to 320 megawatts. Alright? We are going to use these expressions here. In this way, lambda minus 215 plus lambda minus 270 over 2 plus lambda minus 160 over 1.4 equal to 320. And we find a value for lambda equal to 354.2, okay? And if we substitute this here, we find that P1 is equal to 139.1 megawatts. P2 is 42.1 megawatts, and P3 138.7 megawatts. These are the values for economic dispatch. Okay? For the case, this is for the case letter A, when the demand is 320 megawatts. Now let's do the same for the case in which the demand is 200 megawatts. We are going to do practically the same, okay? The only difference is going to be here, okay? And this will be different values here. All right. For the case, letter B, for the case the load is 200 megawatts, we are going to have these expressions here as well, okay? But instead of equaling them to 320, we are going to equal them to 200 megawatts. So instead of writing here 320, we write here 200. And we find a different value for lambda. Now the value of lambda is 300. It will be this. They will be similar steps, but this is going to be different. Okay, the only parameter that's going to be different is the value of the load, the demand. And with this value of lambda, substituting it here, we find different values for the powers. We find P1 equal to 85 megawatts, P2 15 megawatts, and P3 100 megawatts. Okay? This is the exact solution of this equation here, but there is a mistake there. It is wrong, it is not right. Why it is not right? Note that as P2 is less than its minimum possible value, okay, the minimum allowed value is 39, then P2 has to be set at its minimum value of 39. Then instead of 15, which is the optimum, we are going to put 39 here and recalculate. We are going to recalculate for the others. So it is 39 megawatts here, and we are going to recalculate for the others. We are going to remove P2 from the equation, and we are going to solve only for this. But notice that instead of 200, it is going to be 200 minus 39, which is 161. So here it is 161. Solving this, we find a lambda equal to 286. Okay? Now, if we take this value of lambda and put here and here, we find the new values of 71 megawatts and 90 megawatts, and this is the optimum load allocation for letter B. Okay? Thus, the economic dispatch schedule of the generating units with this constraint here, because we have to bear in mind that they cannot assume values less or greater than this, okay? then the optimum schedule is this. Okay, my friends, and this is all for exercise 4. Let's go to exercise 5. Before moving on to the next exercise, let's see the case in which transmission losses are considered. Case 2, dispatch with transmission losses. Transmission losses are expressed by this matrix multiplication here, in which the elements of matrix B are called loss coefficients. And observe that not anymore we are talking about generating units of a single power plant. We are talking about the power outputs of entire power plants here, where there is transmission losses between them and load centers. Okay, we are going to greatly reduce this to for better understanding and deal with a two power plant system. Okay, the level of losses will be P1 squared B11 plus 2 times P1 P2 B12 plus P2 squared B22, observing that B21 is equal to B12. That's why these two appeared here. Okay, now we have our optimization problem here. For optimum dispatch, the penalty factor associated with power plant 1 times the incremental cost of operating power plant 1 has to be equal to the penalty factor associated with power plant 2 times the incremental cost of operating power plant 2, where the penalty factor is calculated by this expression here. Okay, when there are transmission constraints, optimum dispatch will be achieved when the product between the incremental cost and the penalty factor is equal for all plants. Okay, and this is the penalty factor. The penalty factor is a factor by which the incremental cost of power production of the plant is multiplied to account for transmission losses. Alright, this is the theory, my friend. Let's go now to exercise 5. Exercise number 5 now. Consider a power system fed by two plants having the following incremental costs. This is the incremental cost of operating power plant 1, and this is the incremental cost of operating power plant 2. If the loss coefficient matrix is this question, find the optimal dispatch schedule for a system load of 100 megawatts. Okay, my friends, this is the question. Let's go to the solution. As the exercise stated, the load demand is 100 megawatts, then the power plants have to supply this demand. Okay, have to deliver power to this load. But now, differently than the exercises 1, 2, 3, and 4, we are going to consider now losses. Then we have to account for the losses. Okay, so this is the exercise, my friends. For optimum dispatch, the penalty factor associated with power plant 1 times the incremental cost of operating power plant 1 has to be equal to the penalty factor associated with power plant 2 times the incremental cost of operating power plant 2. Okay, this is the condition for optimum dispatch. Since we were given the incremental cost, the exercise gave us the incremental cost. It is necessary only to find the penalty factors. Okay, and we know that a penalty factor can be calculated by 1 over 1 minus the derivative with respect to the power of the losses. Okay, we are going to take the partial derivative of the expression of the losses with respect to the power output. Okay, when we are talking about penalty factor associated with power plant 1, then this is going to be 1 and 1 here, okay? When we are talking about the penalty factor of power plant 2, then here will be 2, alright? And so as it is a function of the level of losses, we have to calculate, we have to find an expression for the power lost. P loss will be equal, as we said, we have to use this expression here, P1, P2, B, P1, P2, okay? We are going to multiply these matrices and find an expression, and the expression using these values here is P1 squared B11 plus 2 times P1 P2 B12 plus P2 squared B22, okay? And if we use the values of B11 is this, B12 is equal to B21, which is this, and B22 is this. When we use the values, we find the expression for the power lost. Alright? And when we take the derivative, we find that the derivative of P loss with respect to P1 is equal to 0.002 P1 minus 0.001 P2, and the partial derivative of the losses with respect to P2 will be equal to 0.0048 P2 minus 0.001 P1. Okay, we are going to use these expressions here to find the penalty factors associated with power plant 1 and power plant 2. Okay, my friends? And when we do this, we find that L1 is equal to, we use this expression here, 1 over 1 minus 0.002 P1 plus 0.001 P2, okay? And we're going to do the same for L2. And using this here, we get to the following result, which is very important. If you arrive at this result, it means that you have understood it all, okay? All right, so P1 plus 200, okay, what is P1 plus 200? It is the incremental cost of operating power plant 1, okay? Divided by 1 minus 0.002 P1 plus 0.001 P2 has to be equal to P2 plus 150 divided by 1 minus 0.0048 P2 plus 0.001 P1, okay? This has to be made equal to this. And the other boundary condition of the problem is that I have already, is this one here, okay? This one here. So these are the boundaries conditions of the problem. This leads to this, and this leads to this, okay? We already know P losses, we have calculated it, and P1 plus P2 will be equal to P loss plus P load, 100 megawatts. Okay, I'm going to pass this to this side and use the expression that we found previously, and we find that P1 plus P2 is equal to 0.001 P1, sorry, 0.1 P1 squared plus minus 0.001 P1 P2 plus 0.0024 P2 squared plus 100 megawatts. Okay? And I cannot solve it by hand. We have to use the computational tool. I used Wolfram Alpha, okay? And after using this computational tool, we find that P1 is equal to 51.2 megawatts and P2 is equal to 56.1 megawatts. Alright? And the level of losses can be measured using this expression here. Okay? P losses will be equal to P1 plus P2 minus 100 megawatts. You simply use this here and this here, and you find that your losses are being 7.3 megawatts. Okay, my friends? This is all for exercise 5. Let's go to exercise 6. Exercise number 6 now. Consider the following power system. This is the power system composed of 2 power plants and a load. The incremental cost characteristics of the power plants are as follows. This is the incremental cost of operating power plant 1, and this is the incremental cost of operating power plant 2 in dollars per megawatt hour. And now the condition of the exercises: if 200 megawatts of power is transmitted from power plant 1 to the load, a transmission loss of 20 megawatts occurs. Alright? Somebody must have measured it and found these values. Now the question: find the optimum generation dispatch schedule and the cost of received power for a load demand of 204.41 megawatts. Okay, my friends, this is the question. Let's go to the solution. As we did before, observe that for optimum dispatch, L1 times IC1 has to be equal to L2 times IC2, okay? What does it mean? It means that the penalty factor associated with power plant 1 times the incremental cost of operating power plant 1 has to be equal to the penalty factor associated with power plant 2 times the incremental cost of operating power plant 2. Alright? Since L1 and L2 depend on the system losses, we need to find an expression for the losses. Alright? We are going to use this. PL, P losses, P1, P2, P11, B12, B21, B22, P1, P2, okay? We are going to use this matrix multiplication, and as the load is at bus 2, so this is bus 1 and this is bus 2, as the load is at bus 2, there will be no transmission losses associated with power plant 2. What does it mean? It means that B12 is equal to B21, which is equal to B22 equal to 0. Alright? So, this matrix becomes this. This is 0, this is 0, and this is 0. This is 0, 0, and 0, okay? Then the losses will be only B11 times P1 squared, okay? Now let's use the condition stated by the exercises for P1 equal to 200 megawatts. We have a loss of 20 megawatts, okay, as the problem stated. We simply use this expression here, and we find that P loss is equal to B11 times P1 squared, and we find that in this case P1 is 200 megawatts, B11 we are trying to find, and the losses will be 20. No, here is the opposite. P losses 20 is equal to B11 times P1. P1 is 200 megawatts. Okay, squared. And in this way, we find that B11 is equal to 0.0005, and P losses equal to 0.0005 times P1 squared. This is the expression that relates the output power of power plant 1 with the level of losses. Okay? We have to use this expression to find the penalty factors associated with each power plant. Okay? This is what we are going to do. For optimum dispatch, we have this, okay? L1 will be equal to 1 over 1 minus the partial derivative with respect to P1 of P loss, and this is equal to 1 over 1 minus, we have to differentiate the expression that we found. It was here, I erased it, and it is going to be the partial derivative with respect to P1 of that expression. The expression was 0.0005 p1 squared, okay? And when we take the partial derivative of this, we find the penalty factor for power plant 1. And the penalty factor for power plant 2 doesn't exist. It is simply 1, okay? L2 is equal to 1 because this expression is not a function of P2, okay? When we take the derivative of a function with respect of this function with respect to P2 is 0, then 1 over 1 is 1. That's why the penalty factor associated with power plant 2 is 1. Okay? After using this expression here, this penalty factor here, and this penalty factor here, we find this equation here. 0.0 0.041 P1 minus 0.05 P2 plus 0.00005 P1 P2 equal to 2. And the other expression that we are going to use is the one that says that P1 plus P2 has to be equal to the power of the load, the demand, 204.41 megawatts. But here we are not taking account of the losses. We have to take account of the losses. Then the sum of the power outputs of both power plants have to supply the load, okay? And there will be an additional power which will be the losses, plus 0.0005 P1 squared, okay? And we have this system of equations. You're gonna need to find a computational tool on the internet. I use Wolfram Alpha, and after using this computational tool, we find P1 equal to 133.31 megawatts and P2 equal to 79.98 megawatts. Okay, my friends, these are the amounts that each power plant will need to supply. And the cost of received power will be lambda will be equal to L1 times IC1, which will be equal to L2 times IC2. You simply multiply one by the other, or you simply substitute these values, and you find $20 per megawatt hour. Okay, my friend, this is all for exercise 6. Let's go to the last question, exercise 7. The last exercise 7. Economic load distribution between thermal power plants. Consider a power system supplied by 2 production units with line losses. That is, there will be 2 power plants. The incremental cost functions of the 2 power plants in dollars per megawatt hour and system losses are: this is the incremental cost of operating power plant 1, and this is the incremental cost of operating power plant 2. And their limits of operation are these. if the system losses can be calculated using this expression, find the optimal dispatch schedule if the power plants are to supply a load of 478.75 megawatts. Okay, so the demand is 478.75 megawatts. All right, my friend, this is the question. Let's go to the solution. As we have already understood, for optimal dispatch, this has to be valid, okay? L1 times IC1 is equal to L2 times IC2. There is optimal dispatch only when this is valid, when this is true, okay? And what does it mean again? The penalty factor associated with power plant 1 times the incremental cost of operating power plant 1 has to be equal to the penalty factor associated with power plant 2 times the incremental cost of operating power plant 2. Alright, so this is the condition for optimum dispatch. Okay, and we already know that the penalty factor of a power plant I is equal to 1 over 1 minus the partial derivative of the expression of losses with respect to the power output associated with this generating this power plant, okay? And we are going to use this expression here. This expression here. Okay, we are going to differentiate this expression with respect to P1 to calculate the penalty factor L1, and we are going to differentiate it with respect to P2 to calculate the penalty factor L2. Okay? When we do this, we find that L1 is equal to 1 over 1 minus 0.001 P1. Okay, we are differentiating this expression here with respect to P1. Now we are going to do the same for P2. We are going to differentiate this expression with respect to P2, and we're going to find L2 equal to 1 over 1 minus 0.0005 P2. Okay, these are the penalty factors as a function of the power output of each power plant. Alright? And we are going to use this expression here. This expression here, which is the main idea behind this. And thus 0.46 P1 plus 781.5 divided by 1 minus 0.001 P1 will be equal to 0.55 P2 plus 1195 divided by 1 minus 0.0005 P2, okay? And this is one of the equations that will enable us calculate the powers. The other equation is this: P1 plus P2 is equal to 478.75, which is the demand, plus the losses. We are not only taking account of the power that has to be delivered to the load. This is the main idea, of course. We don't run power plants for the losses. The main idea is to feed the loads, but we have to take account of the losses, all right? And in this way, the expression becomes P1 plus P2 equal to 478.75 plus 0.0005 P1 squared plus 0.00025 P2 squared. We have to use these two equations. So this is the system of equations that we need to solve to find the powers. I could not do it by hand. I had to use a computational tool. I used Wolfram alpha, and Wolfram alpha gave me this P1 equal to 350 megawatts and P2 equal to 200 megawatts. Okay, my friends? From the values of the powers from each power plant, we find the level of losses. P loss will be equal to 350 plus 200 minus PD, which is 478.75, and then the losses will be 71.25 megawatts. Okay, my friends, this is the solution of this exercise. And this is the video that I wanted to make covering the idea of economic dispatch of power plants. I hope you guys enjoyed the video and above all learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!